Okay, so thank you all for coming. So today we have Sophia Economou from Virginia Tech. She is a professor of physics and the T. Marshall Hahn Chair at Virginia Tech. So she obtained her PhD from the University of California, San Diego back in 2006. And then her work mostly focuses on theoretical research in quantum information science, quantum computing and quantum communication, as well as quantum simulation algorithms. And she's responsible for a very wide variety of cross-cutting contributions ranging from quantum computation, their implementation in solid-state quantum optics, as well as other quantum hardware platform. She's also the director of the Virginia Tech Center for Quantum Information Science and Engineering. And so today she'll tell us a little bit about her work on entanglement in quantum networks. So let's welcome her to the colloquium. Yeah.
Thank you. Is the mic okay? I guess it's control. All right, thanks. Thanks a lot for the invitation and the introduction, and it's great to be back in Seattle. I also was very lucky with the timing. I had a spectacular weather, so I can say I'm, came to sunny Seattle. All right, so this talk will focus on quantum networks, mostly at the kind of the lower level of the stack, so to speak. And specifically about the role of entanglement, how to create it, how to control it, and I don't mind if I don't get through the whole talk. So feel free to interrupt me if you have any questions. Okay, so you've probably heard a lot of talks on quantum information technologies. So I won't give too much of an introduction, but I just want to make sure that we're on the same page. So just to bring up some ingredients that are important, and also define some terminology. So I'll be talking about qubits, quantum bits, which are two-level systems, which can be in, unlike classical bits, can be in a coherent superposition of 0 and 1. Here, I represent them as arrows. Most of the time in this talk, I'll be either explicitly or sort of implicitly thinking about either spins, or photons. So both of these have degrees of freedom that can be thought of as two-level systems. And of course, this superposition is coherent, so the phase between these two states matters. The most important distinguishing feature of quantum bits compared to classical bits is the fact that they can have non-classical correlations, which we call entanglement, and these can persist when the systems are spatially separated, and this is a very important ingredient in all of quantum technologies, and particularly in quantum networks that I'll be talking about. Another features here are that measurement disturbs quantum states and is probabilistic and irreversible, and then quantum systems cannot be, unknown quantum states cannot be cloned. So these elements together play an important role in how we think of processing quantum information and how we design quantum networks. So let me focus a little bit more on entanglement. I'll give you just enough background to hopefully make the talk self-contained and not requiring too much background. So some important entangled states include the Bell states, which are 2-qubit states. One example is written here, and the important thing about these states is that they cannot be written as separate states on each of the quantum bits forming the overall state. And I'll be using a notation that I will define in a moment, but that will look like what you see in the bottom here, where you have circles denoting qubits and a line denoting entanglement between the qubits. And I'll make this more precise in a few slides, but for now, just think of a state of a cartoon like this schematic in the bottom as representing a Bell state shown above. So entanglement is an important resource in quantum communications, quantum computing, and as I mentioned already, it's a distinct quantum feature. So if we try to think about contrasting quantum correlations versus classical correlations, we can kind of try to make an analogy and see where this analogy fails. So you can think of having classically two objects, each hidden inside a box. And you can create this state in a way that these two boxes are classically correlated. So for example, you could put a red object inside one box and a green object inside the other. And there's some probability, let's say 50-50, that the left one is red and the right one is green, or vice versa. One important thing here is that classically, this property is well defined already. So we don't know which object is red or green, but this property is predetermined, right? There's an objective reality associated with each one being red or green. It's just that you describing the system don't know which is which. Unlike this classical case, in quantum mechanics, either one can be red or green, so the property of the color is not determined beforehand. And it's actually not defined at all. So each object alone does not have a well-defined color until you go and you look. So when you go and you look, that's when each object acquires a color and has a well-defined state. And then there's perfect correlations. So if you find the one to be red, the other is green, and vice versa. But these correlations also the one distinguishing feature is that these properties not well defined beforehand. The other distinguishing feature is that these correlations persist in different bases. So what I mean by bases here, you can think of the polarization of a photon as being circularly polarized or being linearly polarized. So it's a different basis. Or if you have a spin pointing along the z direction or the x direction. And if we want to push this analogy to colors, you could ask, you can define a basis by looking at colors that are across each other in the color wheel and say, instead of red and green, I could ask, is this object orange or blue? And these correlations would persist no matter kind of which direction I look at. So these two properties together kind of distinguish, in a more kind of colloquial way of describing it, the quantum case from the classical case without bringing in math or inequalities or anything like that. So this is a property we want to be able to control and make use of in quantum technologies. So what we can do if we can kind of harness these properties is create quantum networks. And if we have quantum networks, we can run various applications on them. For example, quantum cryptographic applications. Things like synchronization protocols, extending the baseline of telescopes, and also accessing quantum computers in a secure way. So right now, the way you can access cloud quantum computers or quantum processors is you send classical information over the internet. The protection there is whatever your classical network has. And then whoever is running this quantum computer has access to your information, right? So your information is classical. It's a set of instructions that reaches the operator of the quantum processor, and that person or that computer can run your quantum algorithm. If you have quantum networks, you can actually send quantum information securely, and you can send the set of instructions for your quantum algorithm in a quantum secure way over a network. So this means that you can access in a secure way, meaning that the information you're trying to send and the algorithm you're trying to run are also secure. And if you're interested in reviews, I can recommend these two. One is by Stephanie Wiener from a few years ago, describes the different types of protocols and different stages of a quantum network. And more recently, my co-authors and I have written a longer review describing also kind of the physical processes and the different generations of quantum repeaters in a more comprehensive way. Okay, so to actually create a quantum network, we need to worry about the limitations that the physical objects that make up our quantum network bring. So let's just take a very simple primitive where the two parties are trying to share an entangled state. I mentioned already that entanglement is a resource. We'll see a little bit more about that. But for now, let's just say that they want to do the simple thing. So the simplest thing you can imagine is that one of the two parties, let's call the party Alice, creates a Bell state. And you can imagine that this Bell state is made of a photonic qubit and a matter qubit, or two photons. It doesn't matter for this example. And then Alice sends the one photon over some channel to the other party, Bob. Of course, when you do that, there's attenuation, and this photon can be lost. So you have to worry about that, and of course, classically, people worry about that, and what you can do is you can measure the signal, amplify it in intermediate stations, and send it back down the channel, et cetera. Quantum mechanically, you cannot just do that simple. This protocol doesn't translate as straightforwardly because you cannot just measure quantum states without disturbing them. And somehow we have to deal with this problem. And the way we can deal with this problem is, the simplest way you can deal with it is to put someone in the middle. Then you cut your channel in half. And let's call this person Charlie. Charlie can create a Bell pair. So now the photons transverse half the distance than from Alice to Bob. But of course, this is not straightforwardly scalable. We need to worry about what happens if also from Charlie to Alice and Charlie to Bob, this distance is long and the fiber attenuation is significant, which is, of course, a practical case. So let's imagine this, which still doesn't solve the problem but gets us there. So Charlie can instead create two Bell states. And then there's a very important primitive that is known as entanglement swapping, where Charlie in the middle has these two Bell pairs. He can send half of one Bell pair to Alice, half to Bob. And then he can make a measurement locally in his station. And if that measurement is done in the correlated basis, so you can think of doing something to entangle these qubits and then measuring them, then he can get a Bell pair locally. And now the entanglement that existed in the two pairs is transferred out to Alice and Bob. So this is a very important primitive in quantum networks, this projective measurement in the correlated basis. And it's also known as heralded entanglement because upon this measurement, you know that the other qubits are entangled. All right, so before I show you how you can scale this to large-scale quantum networks, let's see how you would actually implement it with physical systems. So you can imagine some physical, let's say an atomic quantum system or a color center in a solid that has two lower levels, which you can distinguish, that you can think of those as the qubits, the qubit states of this physical platform. And let's say that's a spin state, so spin up and down. And then there exists some excited state that only couples to one of them. So the X here is meant to show that that transition does not happen and the other one does. So what you can do is you can excite this up state to state E, and upon decay, a photon comes out. Now, when this happens, what you get is you can get a spin photon Bell state. So you can get you get a correlated state, entangled state between the spin of the object that emitted the photon and the photon that comes out. And the degree of freedom of the photon in this case is the 0 or 1. So it's the occupation number. So whether there's a photon in that mode or not. So there's many ways you can implement this. I will mainly be talking about defects, color centers such as the Envy Center in Diamond, that there's a lot of work here on. And a lot of the work I'll talk about applies to pretty much any color center, but it can also be extended to other systems. So these are systems that have a nice optical interface and have a spin that you can use as a memory. So I'll focus on those. All right, so let's narrow down on the MV center. Again, I'll be talking about this as a paradigmatic system, but a lot of the things I'll talk about are more general. So you can imagine the diamond lattice, which is shown here in the schematic. So this is just a unit cell of the diamond lattice. So of course, this repeats. And locally, so the dark gray circles are carbon atoms. And then locally, there's 2 carbon atoms missing. One of them has been substituted by nitrogen. And its neighbor one of its neighbors is just vacant. There's no carbon there. So this complex is known as a nitrogen vacancy center in diamond. And it has an atomic-like structure. So on the right side of the slide, you can see that it has these lower levels, which 2 of these can be taken as a quantum bit, a qubit, and also has this optical interface. So photons can come out in the way I showed you. And this system can be controlled. It can be controlled optically when you want to measure it or prepare it. And you can also do unitary gates by directly driving the qubit transition. And you can define your qubit by choosing any of these 2 states. It makes sense to choose the 0 and one of the 1 states, as I'll show you in a moment. So the way we can entangle 2 qubits located in 2 different diamonds is shown as follows. So imagine that each of these diamonds is very far away from each other. And each of these emits a photon in a way that you create a Bell state between the spin qubit that's located in the diamond and the photon that's emitted. And then these photons are guided, let's say, through an optical fiber each in a common location. And in that common location, you do an experiment where you pass these photons through a beam splitter, and then you measure them. And this measurement for photons is probabilistic. Let's not worry about that quite yet. But let's assume that this measurement of the photon succeeds. When that happens, then you have created an entanglement between these 2 objects that never directly interacted. So you're using as a resource the entanglement that each of them has with the photon. You're bringing the photons together, and then you're transferring the entanglement between these spin qubits. And by the way, if you have any questions, please interrupt me. Yeah?
So any question, so when you mentioned this entanglement swapping protocol, and you divide, let's say, a fiber into half, then if you assume that the memory at the center node is infinite, so then just by repeated division you can get to the lot. But if the memory is finite, then you again get back an exponential.
Yes. So the question was, I'll show you in a moment how you break up the long distance into smaller pieces to basically concatenate this. And the question was that you have to make assumptions about the memory, how good the memory is. Otherwise, this doesn't scale well, and that's absolutely not the case. All right, so there's been experimental demonstrations of this, more than 1 at this point, but I'll highlight this one from the Delft group in the Netherlands, where you can see an aerial picture of the Delft campus, and A and B are 2 labs. Each of them has a diamond with this spin qubit in it that's very well characterized and controlled. And then the photons come out these yellow lines and come together in lab C, where this joint measurement happens. And this process entangles qubits A and B that you can see here are more than 1 kilometer spaced. But of course, that's not enough. You need, as mentioned, to concatenate this process. So now the way this works, at least in principle, is you have these nodes where you emit the photons, shown in the blue. And then you have these intermediate red nodes where you measure the photons. And let me show you in a more abstract way how this works. So in the middle, the blue ones are in the same node. The photons are shown in green here. And the BSM denotes Bell state measurement. So that's where the photons are measured. When that measurement succeeds, then you connect, like shown over here, you entangle qubits that are far away. And now you've cut the distance a lot. So you can, in principle, make these nodes very closely separated, several kilometers away. And to go back to the previous question, here you're assuming, because this process is probabilistic over here, this green qubits coming together and being measured, you're emitting them until you can get this to succeed. But in the meantime, the ones that have succeeded, those memory qubits that are entangled with them, the blue qubits, have to remain coherent. So they should retain this information until all of them succeed, essentially. And at that point, you measure the ones that are in the same node, again in a Bell state. So you also swap that entanglement. And then you basically have swapped out all the entanglement in the middle places, and you create this long-distance Bell pair. Right? So there's issues with this process being probabilistic, the memories not being perfect. You can do more tricks, like you can multiplex at the nodes. You can do some error correction. I'm not going to go into too much of that detail, but a lot of it is discussed in this review. Yeah.
Even in this protocol, I guess I'm a bit confused by. So that even if you assume that the memories are perfect, then don't you pick up another exponential in L just because you keep the Bell measurement at every point to succeed? Like if I chop the entire fiber into n pieces, then I need I would declare this protocol to have succeeded if all the Bell measurements. But there is some loss which would lead to a fail, right?
Yes. So you can do some multiplexing. So you can emit multiple photons simultaneously.
Okay.
So you can trade off temporal with spatial resources, essentially.
So the way I should think about it is there are like multiple blue nodes
Yes.
at each site, and then we just need at least one.
Yes.
On each thing to succeed. Okay, so the number of nodes that you need would be polynomial.
Yes.
Okay, thank you.
Yeah, so this is a very, very simplified kind of schematic of it where I don't worry too much about all these issues. And there's a lot of imperfections that can come in. And it's an active area of research of which paradigm is better. Probably this is not the best way you want to do it. And I'll show you alternatives in a moment. But this is something that this approach is something that people still are trying to do. So I'll focus on this first. All right, so let's go back to the MV Center as a prototypical system. And as I mentioned, you need at least 2 qubits in each node, right? At least 2, ideally more. Of course, there's just one MV Center in the schematic, but we have an additional resource. We have additional qubits that are sort of given to us in some sense for free in this diamond lattice, which are isotopes of carbon that have a total spin of a half. So these are pretty good qubits in the sense that they are long-lived, and they occur with a probability 1%. So there are enough of them to be able to do something non-trivial with this resource. And this is how, if you can control them, I'll get it to in a moment to how you can control them. This is how the protocol would now work, right? So this is one of the nodes in this network. This is 2 of the nodes in the network, right? This is one, and this is another one. And now you again run your entanglement swapping protocol. So you send the photons, they meet in this beam splitter, you measure them. Again, this might not succeed. But if it succeeds, then you transfer the quantum state from this optically active system, this envy center qubit, which is in purple. Somehow, let's not worry about how yet. You transfer the state to a nuclear spin, one of the nuclear spins that's nearby. And when you do that, you get this orange connection that's shown here between two nuclear spins in different diamonds over here. And now the envy center spin, the electronic spin, is free. It doesn't carry any connection anymore, right? This purple line has been turned into this orange one. And it's free to be able to do another photon emission followed by this measurement. So now you can connect it to something on the other side. And you can combine this at different nodes and create an entangled state that's delocalized over nuclear spins located in different diamonds across a long distance. And people have done such experiments. This relatively recent paper showed a 3-node network, in quotes, because this was in labs, basically in the same building. You see the longest distance here is 30 meters. But it was a proof of principle demonstration of a genuine 3-qubit entangled state, known as a GHZ state, shown over here. So you can think of this as a way to generalize the Bell state for 3 qubits. And they did some measurements of different combinations of Paulis, where they showed that with a somewhat high fidelity, they had the state they were going for. OK, so now let's go a little bit kind of lower in the stack and think about how does this physically implemented, right? So physically, we have some Hamiltonian. These nuclear spins are located far enough from the envy center that the interaction is dipolar. So it has the form shown in the top line, where m is the magnetic moment. So it's essentially the spin. And it has the interaction shown there. Now, you can massage a little bit this expression and rewrite it in terms of Pauli operators, which is how we like to think of things in quantum information. So you can write it in the way I'm showing the second line. So you have a term. So the first operator refers to the envy center, the electronic part. And the second one refers to the nuclear part. And this is just one envy center and one nuclear spin. And there's 2 hyperfine numbers, this A parallel and A perpendicular, which characterize the interaction. Right, so that's the physical interaction you want to use to somehow create these entangled states and entangled gates. Right, so again, just what I told you. And one thing I should mention here is, if you remember, the envy center has 3 states in the lower manifold, and I'm only keeping 2 to create a qubit. So anytime I write down a Pauli operator, it lives inside this 2-dimensional manifold of the lower levels of the envy center. And one of them is the 0 state, which will be important, and I'll show you in a moment. So now we have this physical interaction. We can use it to create entanglement. I'm slightly massaging this expression again by explicitly writing it in the following way. The objects shown in the brackets, right, these first types of objects here, these projectors, are projectors on the electronic spin. And the orange ones are on the nuclear spin. So basically what this tells you is that when the envy center is in the state 0, the nuclear spin see a Hamiltonian H0. And when they're in state 1, the nuclear spin sees the Hamiltonian H1. So this Hamiltonian has a conditional form. That means that when I look at what type of evolution it can create in time, the evolution is basically exponentiating this Hamiltonian operator. It will inherit the form of the Hamiltonian. So this conditional form will be transferred to the evolution of this system. And this is kind of nice because it's the way we think of conditional logical gates in quantum computing and quantum technologies in general. So what this and this is a 2x2 operator. It's a rotation operator. So what this operator tells us is that when the MV spin is in state 0, I'm going to have some evolution, some rotation by some angle and around some axis. When it's in state 1, I'm going to have a different one. Now, and that's a basis to create, for example, controlled NOT gates, which are also, in turn, the basis for entanglement. However, we have to deal with some challenges here. So when we think about a quantum computer or a quantum processor, we generally think that I can do a 2-qubit gate when I want to. And at a different time, I can do a single-qubit gate, and then I can combine these gates. But my gates are switchable, right? I can kind of do my gate and then not do my gate, stop doing it. And in a model, if you're played at all with the IBM, for example, interface, you're sort of implicitly assuming that things are done instantaneous in time. That's not the case, but it's a good approximation to think of your circuits that way. Here, right, this is a very different, not too different actually if you look under the hood in the IBM, but here it's very kind of in your face, the fact that all the nuclei are coupled all the time to your MV center. So your interactions are very much non-switchable. They're always on. And moreover, in the simplest case that I will be focusing on and that many experiments focused on, you are only driving the electronic spin. You're only driving 1 qubit. So you have this always on, sort of a very inherently many-body kind of system that where you want to control as much as you can, and everything's controlled through the central 1 qubit. So you need to do something to be able to make this problem tractable, because ideally, you would like to be able to do gates that only affect 2 qubits at a time. Your central qubit, which is this purple, the MV, and one of the nuclear spins. Yeah.
So I guess maybe I'm a little bit behind. And so the nuclear spins, the reason why we want to use them here is because they have more memory. Like if they were not present, would
you want to have more than 1 qubits, right? So the question was, why do you want the nuclear spins at all? So for example, here, at each node, you want to have more than 1 qubits because you use 1 to send.
Like you have like 2 MV centers.
You could have 2 MV centers, but then you have to worry about how do you do the gates between the 2 MV centers, which you could also assume a model where they're always on, or you could also do locally photon-based. Yeah, in some sense, but one is that the nuclear spins are there. So to some extent, they create decoherence if you ignore them, right? Unless you purify your diamond. Or if they're there, you can use them. And then you have more of them as well. So you can even think about doing some kind of error correction, which people have done, at least proof of principle demonstrations of.
So the setup that you're imagining is that every pair where you have your 1 MV center and like many nuclear spins.
Yeah.
And then the MV center is just like a mediating.
Yes. So that is called a broker. Yeah. It's the one that basically has the optical activity, and the other ones are your memory qubits. Yeah.
So I guess maybe one question, maybe slightly more practical, is that then I would imagine that the number of, like as you mentioned, that the number of nodes that you need at any one location in your repeater protocol would generically scale with the length. Right? Just to avoid.
Sorry, the number of nodes?
So for instance, like as you mentioned that if I just take this setup with 1 node, or sorry, 1 pair per node,
yeah,
then the probability of a successful, let's say, long-range entanglement being created is still exponential with the length, right?
Yeah, so that's one thing. I would say there's an even more important reason you want more. So in this case, I would want the MV and actually 2 nuclear spins at least. aside from the multiplexing question, I would also want to be able to not store information in the MV center while I'm doing these attempts of spin photon entanglement.
But
So,
in terms of the multiplexing, that seems to be a necessary ingredient. I don't know if there's a way around it.
right, so you could have different samples, right? They don't all have to be in the same.
I see.
Yeah.
So okay, so you would just avoid the need for the NV centers to interact.
Yes, I mean if you have different ones, you would need some local Bell state measurement of photons, right? If you have two different.
I see, I understand.
Yeah. Okay, but the premise here is that this is the system you have. You could scale it up in various ways. But since this is a resource that's sort of given to you for free by nature, we want to be able to harness it as much as we can. Otherwise, because all these nuclear spins would otherwise interact anyway and cause decoherence, right? So, yeah, question?
The NV only couples to the nucleus, the nearest nucleus, right?
No, it actually couples to a whole bunch of them. So it's a dipolar interaction. Generally, it's not a contact. They're far enough. But it's a weak, of course, the interaction decays as you go further away. So you also have to deal with that, right?
Density is high enough, the carbon-13 density is high enough, so we can find enough neighboring NVs around the couples.
Sorry, could you repeat?
So is a carbon-13 density high enough so that there's...
Yeah, I'll show you a picture. Yeah, I'll show you a picture from the experimental group. Yeah, 1% sounds low, but it's not that low because you have this three-dimensional structure. And actually, what I'm about to show you kind of speaks, I think, to what your question is. So let me show you how people deal with this. So the first question is, how do I deal with the fact that I have these always-on interactions? Something similar has been figured out by people in nuclear magnetic resonance, which is, let's say I have a spin that precesses under a magnetic field, and there's a stochastic element, some noise in this magnetic field. If you assume that this is a constant during your experiment, what you can do is you can actually do a pulse that flips the spin in a way that you can think of this as in an ensemble picture where you have a bunch of spins, each seeing a slightly different magnetic field. So there's some that see a strong magnetic field and they precess fast, and some that see a slow magnetic field, they precess slow. And then you can do a pi pulse and flip them in a way that you advance the slow one and you delay, you advance the slow one and you delay the fast one in a way that at a later time they meet up at the same point again. And this is called spin echo. It's a well-known technique in NMR that's also used in various quantum information protocols. Here you have to assume that the noise is unknown, right? This inhomogeneity is unknown, but it's constant. Meaning during this time that it takes to run the experiment is a constant. Now you can have more general types of decoupling sequences, one known as CPMG after the initials of the people who came up with it, where you can have multiple pulses, not just one as shown here. And this actually does better than spin echo. So I'm not going to go too much into why this works, but just introducing this idea of a sequence of pulses that basically averages out unwanted interactions. That's a way to think about this. So that's what people have been doing for at least 10 years to deal with this problem in the system. So the idea is that you are driving your central spin, your MV, with pi pulses that have some spacing between them. In this case, I guess the spacing is t/2. And you repeat the sequence multiple times. And the things you have to play with here is the time, the separation between your pulses, and how many times you apply the sequence. So if you apply such a sequence, this is called the decoupling sequence. So it kind of gets rid of the interactions, similar to the spin echo. But if you pick your timing right, you can actually not decouple a particular nuclear spin. And that's what's shown here. So you can choose your T to be in resonance with the wanted qubit, the one you want to couple to. And that offers you some sense of selectivity. So what you're doing is you're decoupling generically your qubits, but you're only coupling one, ideally. And this is a picture from a paper of the Delft group where they did this experiment more than 10 years ago first. And don't worry too much about what the y-axis is. It's some kind of signal that shows you these resonances. So basically, it tells you that for different times, you have these dips that correspond to different nuclear spins. So this is a way to select the qubit you're interested in. And of course, you pay the price of time, right? You have to repeat the sequence over and over. And now you still have the knob that's given by this capital N, which is how many times you repeat your unit of your pulse sequence. And by playing with this N, you can actually create a target rotation on the nuclear spin that you are targeting. So you can control which gate are you doing. Yeah.
To pick this T, you need to know the...
You need to know, you have to have your system characterized.
Okay, so you're assuming that the Hamiltonian is known.
The Hamiltonian is known.
Then I get
Yes.
the sequence.
Yes. And they have done painstaking work in Delft. I think I have a slide. They have characterized, they have a specific sample where they have characterized 30 or more nuclear spins. Yeah, absolutely. Right, so then now by controlling this extra knob, your N, you can create a control NOT gate, which is the workhorse of quantum information processing. It's the thing that helps you create entangled states. All right, so you want to make these two Rs, these two rotations, different. So you want, if the electron is in state 0, to do a certain rotation, and to do sort of the opposite if it's in state 1, as is shown in the schematic. However, this does not work perfectly, right? Because dynamical decoupling, as the name implies, decouples, but it doesn't decouple perfectly. So there's going to be some nuclear spins. You can imagine a nuclear spin that's really close to the one that has parameters very close to the one that you're selecting, for example. Intuitively, you would not decouple that very well, right? So even though generically we say these are decoupling sequences, in practice, they're not going to work perfectly all the time. So the way people were dealing with this was to select some sequence based on this model of one nuclear spin and your central qubit. You know, find good parameters for it, and then go and check all the other ones numerically, right? But this is a very, not a very efficient way to do it, and you can't, for a large system, you cannot basically simulate it. What we realized, actually, my student Eva Taku, that I'll show you in the acknowledgements at the end, what she realized is that you can actually include all the nuclear spins in the description in a systematic theoretical way. And I'll give you a little bit of an overview of how that is done. So the first step is to realize that the evolution operator for the whole system maintains a relatively simple form. This projector on the one state of the qubit, the central qubit, tensored with some evolution on the nuclear spins, plus another projector on the other state, tensor with a different evolution, is a very non-generic form, right? Because you see you have projectors on the central spin. You don't have zeros and ones mixing. So this makes a very big difference. And what you can do is you can start asking now, if I allow the system to evolve under some pulses, which is what I'm doing to the electronic spin, how much do different parts of the system get entangled with the rest, right? So ideally, if I only wanted 2-qubit gate, I would want my central spin and one of the memory qubits to get entangling evolution, and the rest, nothing to happen to them, basically. So you can formalize this through something called one-tangle. where you're looking at your system, you're tracing out one of the qubits, and then you can average over different product states to get a sense of the entangling power of the gate itself and not just a state. So you can generalize the sense of one tangles for your gate, which is the U, the evolution we're looking for. And then you can start asking this question by tracing out or by selecting out a particular nuclear spin. So sort of the breakthrough here was to realize that you can get simple analytical expressions because of the form of the evolution operator. So you can go and you can solve the problem of the central spin, the MV spin, and one nuclear spin, and get some expression. And then when you, for example, trace out the, look at the one tangle of the MV spin over here, in the many-body system, the expression is in terms of the having solved the two-body problem separately. And this is exact. There's no approximation here. So this makes your life much easier because you can solve the two-body problem, and you have essentially solved the many-body problem. And the things that enter here, I'm just going to flash this because it's maybe a little bit too technical for a colloquium, but the quantities, these G's that enter here, are quantities that characterize how entangling a two-qubit gate is. So if you have some generic two-qubit gate, it will have entanglement in it, and it could be universal for quantum computing. Generically, it would be. But you want to know what kind of entanglement can this gate produce and how much, right? So you can have gates that are locally equivalent, up to single-qubit gates equivalent to a C0 control NOT gate. For example, a control NOT gate and a control Z gate belong in the exact same entanglement class because they're related to each other with single-qubit gates. There exist other gates, like square root swap gate, which is in a different entanglement class. It can also create entanglement. It can also create a Bell state. But you cannot get to a C0 with just adding single qubit rotations, right? So there's this way, this machinery to classify two-qubit gates. So the key quantities that enter this expression are these quantities that classify the two-qubit gate. And that's all this slide says. I think I'll skip the details. It's essentially what I told you.
So this epsilon quantity that you have, it classifies these different gates that are not connected by
this. Yes, so this epsilon will be different for different U's. Is that the question?
Yeah, no, so is it the same for like, so it would be the same for C0 and
C0 and CZ, yes, because the G is the same. Yeah, but for different classes will be different. Yeah.
So but like, what is the implication of this on the original problem? Because I thought the goal was to be able to design pulses in such a way that we don't couple different nuclear spins.
Right. So now you have a way. The question was, the goal is to decouple nuclear spin, right? But now you have a quantity, something that quantifies how much they couple, and that expression is analytical. So for different pulse sequences, you have an analytical expression as to how much each of these memory qubits couples. So you can optimize your problem in a way. I mean, you need some numerics at the end to do this optimization part to select out pulses. But now you don't have to solve a many-body problem classically. Does that answer your question?
I see.
Yeah.
So what you're saying is that, okay, this we're computing these G's, which is just this
You're computing the one tangles in terms of the G's, but for the whole system. Yeah. If you had maybe I should say, if you have a generic Hamiltonian, this is not going to be a tractable problem. Yeah.
So, so what you're saying is that now given a control sequence, I will get a G, right? And then maybe you will frame a cost function. So maybe then you'll frame a cost function in terms of the pulse.
Yes.
And so let's say when you find a pulse sequence that minimizes this cost function, but that's still like an average case measure, right? So even if that is small, it is possible that you still have large interactions, right? Because for example, this is, what I don't think I can answer later, but what I don't see is that how, if I just define like a fidelity metric, so let us say, finally I'm interested in applying the gauge between nuclear spin 1 and NV, in presence of all the other n minus constant. So that is once I can define a precise fidelity metric there. So let's say how close, given a pulse sequence, how close is my gauge to the target gauge. But this is like an average gauge, somewhat different fidelity metric. So I'm wondering like how are they doing?
I wouldn't call this an average fidelity. You characterize, you look at all the nuclear spins that are significantly coupled, which again, you have to put some threshold. What do you mean by that? Let's say all your system qubits. And then you say for each of them, how much does that one couple? So you can simultaneously, I'll show you, you can make all of them less than some threshold.
So maybe another thing maybe I can ask, like let's say this epsilon or like the cost function based on this epsilon is small, then is there an upper bound of the fidelity metric based on this epsilon?
I think there is.
Okay.
We have not done that, but I think there should be, yeah. Yeah, you can get the fidelity for this, yeah. Yeah, so let me just show you maybe a few results. So now you can you can create some sequence that couples one target qubit. And now you can look at in this 2D landscape of different coupling parameters, which ones are more coupled and which are less coupled. So you can select your sequence in a way, if your goal is to decouple all of them except for one, you can systematically do that. Another thing is you might want a bunch of them to couple simultaneously in order to, instead of doing a 2-qubit gate here and then another 2-qubit gate here and a third one here, which would take time, you could do a simultaneous multi-qubit gate in a way that it decouples, let's say, 4 qubits and it couples 4, as in this picture here. So again, you can put some threshold for your one tangle, this quantity we calculate, and then figure out which ones are strongly coupled and optimize your sequence in that way. And this is, I think, answers most question, which is these points here are from the Delft group. They show the C13s that are strongly enough coupled that they consider. And you see they're, in the scale, they are a lot, right? There is non-trivial. I should also mention that because you're doing this dynamical decoupling, you can considerably couple to qubits which have a hyperfine coupling that is relatively weak compared to the dephasing of the electron because you're applying dynamical decoupling. So this is what they show here. They have characterized the system very well. And this goes to your question, right? They know very well where the nuclei are located and what the hyperfine parameters are. They're doing some fancy 2D spectroscopy I'm not going to talk about, I'm not an expert on. But they have figured out very well how to characterize. And this is from a published paper from 2019, which is 27 qubits. I think now they're at 60 or something. So they, it's very impressive. Of course, this is their one sample. They have characterized really well. So what we did for this work, we examined more than 100 different decoupling sequences. And we have this cutoff that tells us how much can we decouple these couple the target nuclei and decouple the others. So then we look at different cases out of these, where we take a dynamical decoupling sequence that aims to couple a particular nuclear spin. And we also look at how many others does it couple at the same time significantly. So you can have a different, in the x-axis, think about different dynamical decoupling sequences, different pulse sequences. And in the y-axis, the number of nuclei that significantly participate. And then you can also ask, what is the gate time and what's the gate error in this case? And for this, we really looked at my student went and picked all the numbers from their experiment. So this is very tailored to this particular sample, right? And this particular MV inside that sample. But you can do this efficiently for any, and it doesn't have to be an NMV, it can be some other defect. Right, so this is a well-defined recipe that you can run to efficiently solve this problem. Yeah, and all this is contained in this paper, and later we have a follow-up work where we use a tool that's called entangles, which sounds very similar to untangle, but it's mathematically a different way to characterize many-body entanglement. And that metric also tells you what type of entangled states you have. So if you want to do GHZ states, that entangle has a different value than if you have something called W states, which are also generally many-body entangled. So this way, you can really create the state you want up to single qubit gates. So maybe I'll pause here if there are any questions. OK, so maybe I'll take just a few minutes. As I went a little bit slower than I was anticipating, but I'll just show you some highlights from the second part of the talk. I'm not going to go through it unless there's any questions, in which case I can just stop here. OK. So as you correctly pointed out, there's remaining challenges, right? This multiplexing, how things scale. You have to do error correction. You have to do entanglement distillation. The entanglement won't be perfect. So there's a lot of caveats with this type of quantum repeaters. And for that reason, people have come up with other ways of trying to do quantum networks. And one way that's very promising is doing all photonic, so trying to get rid of the memories altogether, because the memories bring in imperfections, right? Spin qubits decay. They're not perfect memories necessarily. You need to control them well, et cetera. I'm not going to entirely get rid of the matter qubits, but you can think of using them in a more supportive role rather than as centrally as memory qubits. So there's one way where you can create entangled states of photons in graphs, which are particular types of entanglement. And then you can send the photons from these graphs to nodes. And because these graphs are multi-photon states, not just one Bell state, you have redundancy built in a way that you can have multiple shots at Bell state measurements. So this paradigm addresses to a large extent the fact that the Bell state measurements are probabilistic. You're giving your state enough redundancy to be able to repeat them. And you're also building in some error protection, specifically photon loss protection. So these are some kind of multi-photon resource states that can address the problems of memory-based repeaters. So I have some definition of graph states. I think I'll skip that. Just think of this as a generalized, general entangled states of many photons. And these states have nice properties under measurement. So we know very well how they behave. And we can use this to create entanglement. So let me just show you a cartoon of this. So you assume now that you have these nodes where you can create these graph states. These are the blue nodes over here. And then you have some measurement nodes where you send the photons. And now you see in your blue node, you have nothing left. You don't have memory qubits left, unlike the first type of repeaters I showed you. So now you try all these Bell state measurements. And then for the ones that succeed, you see you have these arms sticking out. If the Bell state measurement succeeds, then you go and you measure the neighboring qubits in the correct basis. Correct basis means in a way that you essentially extend the entanglement out. And you get rid of the qubits that are not connected to those. So if you do that, you can create an entangled pair, similarly to what I showed you so far. You need to do some protection, to build in some protection. So I'm not going to get into details of this, but there's a way to build in loss tolerance into your states, so that if you lose photons, these protocols can still work. I think this is trying to send me a message. So I'm going to speed up and just mention that it's very inefficient to create these states using linear optics, which is what people have been mostly doing for a long time. For example, to just get a 3-photon GHZ state, the probability is 1 over 32. So the vast majority of the time, this fails, and you have to try again. So in my group and other groups, what we're trying to do is use quantum emitters to generate these resource states. So now we put more mild requests on the quantum emitters. We don't want them to be perfect memories. We want them to be good enough to generate our resource state, and then that's their use for the network. And this is a schematic where you can think of creating a state on matter qubits and transducing it or mapping the photon onto photons. Or you can think a way of sequential emission of photons out of matter qubits in a way that they come out in an entangled state. So I think with that, I'm just going to flash some experiments just to show you that people have been trying to do this using different types of platforms, either quantum dots or atomic systems, even experiments with superconducting systems. And let me skip this. We have a way of doing of producing graph states for quantum repeaters. I'm happy to talk offline about, and a way to build in loss tolerance. And more recently, I just want to highlight this paper, and I'll finish up for questions. We have a systematic way where if you start from any graph, any photonic entangled graph state, we have a recipe of reverse engineering the process and telling you how many emitters you need, so the minimum number of emitters you need, and how to control them such that you can generate the state. And this is a reverse engineering approach where I start with my final desirable state, and I kind of go backwards, and I go toward a disentangled state. And then by running this protocol in the reverse direction, you actually have your circuit. So I'll skip that. And this scales well. Both classically went to find this protocol. It scales polynomially, and the quantum resources scale polynomially as well. All right, so I'll just put up my summary. The focus here was quantum networks. Two different types of networks. I focused much more on the memory-based one, but there's one also based on all photonic. And I'd like to make sure I acknowledge my collaborators. Most of the work you heard about was by a student Eva Taku, who's an amazing PhD student who did the work I elaborated on. And then the graph state work was led by Bikun, who is now a postdoc in Liang's group. And a lot of work has also been done by Paul Lair, who's now at Quandela, and co-supervised with my collaborator at Barnes. So thank you.
I guess we are already over time, but maybe one quick question if anyone has. Okay, I guess not. Oh, okay, yeah.
So you mentioned that the BSM measurements were probabilistic, right? What is the acceptable error rate for the Bell state measurements?
So the Bell state measurement succeeds 50% of the time. Generically, you can do things to make it to boost that, but you can make everything work with that 50% of the time. It's just that you need more resources.
Okay, well, let's thank the speaker again.